Hi everyone. Good evening to one and all present here. This is going to be the second weekly live session on the NPTEL course of Remote Sensing Principles and Applications. This is brought to you by the NPTEL and the SWAM initiative. I'm Abhishek Chakraborty, a PhD student under the Prime Minister's Research Fellowship Scheme at the Interdisciplinary Center for Water Research from IISc Bangalore. And this course has been taken by Professor Ishwar Rajshekharan from the Department of Civil Engineering at IIT Bombay. So this is going to be the second weekly live session by me on this course. Uh, so before proceeding to today's uh, solved examples, I would just give a brief information. The video recordings of the session will be made available on the YouTube channel. I will be sharing the link in one slide from now. The files relevant to the sessions will be made available through a Google Drive folder. The files and the video recordings will be made immediately available after the class, and the images, if they have been taken from the internet, are solely for educational purpose. We don't aim to plagiarize some copyrighted work. So this is primarily the YouTube channel on which I will be recording the videos. I've already created a playlist which contains the first lecture from the weekly live session 1, and it was around a 1 hour 57-minute video which I had basically presented to you on last Friday. And this is the link, the spreadsheet link, which contains the links, Google Drive links for both the YouTube video as well as the Google Drive, which would contain the slides with the illustrations. So we would be first of all solving a few questions today, and then we will be moving into some of the concepts which were discussed in the class by Professor Ishwar, and then we will again proceed into solving some more questions. So the first question is basically the total solid angle subtended by a sphere at its center is it 2 pi steradian or 4 pi steradian or pi steradian or pi by 2 steradian? So steradian, if you are not aware of, sorry. Okay, so yeah. So steradian, if you are not aware of, is basically used to measure the solid angles. It is primarily the solid angle subtended at the center of a sphere, at the center of a sphere of radius r. Just a second, I would need to admit something. Yes. Hi Nirbhay, please unmute yourself. Please mute yourself for the time being. If you want to ask anything, you guys can feel free to unmute yourself and straight away ask the question. Okay, so a steradian is primarily nothing but a solid angle which is subtended at the center of a sphere R by. Okay, another person is trying to enter the room. By a section of its surface area of magnitude equal to r squared. So it basically translates to the thing that the surface area, we know that the surface area of a sphere is always 4 pi r square, where r is the radius of the sphere. So we can say that there are 4 pi steradians surrounding a point in space. So since there are 4 pi steradians, the accurate answer would be B, the 4 pi steradians. However, I mean, if you want a formula for it, the formula can be like this. So the solid angle is given by area subtended, that is the surface area, divided by r square. So let us suppose this omega is the solid angle, the area subtended, let us suppose surface area is delta s by r square. So the total surface area we know very well is 4 pi r square of a sphere. We divide it by r square, we get 4 pi steradian. So the answers are same by both the methods. You can either use a formula or you can go through the statement. I will take a few additional questions on this concept itself by altering it a bit. Yeah. So an additional question would be like, what is the solid angle subtended by the periphery of an area 1.5 centimeter square at a point situated symmetrically at a distance 5 centimeter from the area. So we are given that the area is the surface area is 1.5 square centimeters. The distance is also given. Distance is nothing but the r is 5 centimeter. So we want to know what is the solid angle. So solid angle, we can straight away use that equation. Area by the radial distance square. So area is 1.5 square centimeters, the radial distance is 5 centimeters square. So it will come out to be 0.06 steradians. Let us take another example, a very valid or relevant example for this course. So the solid angle is only valid for 3D figures. Like say cone or sphere, whereas a plane angle you all know very well, you are quite familiar with it. They are valid for 2D figures. Like let us say circle, arc, etc. So the plane angle, let us suppose this is a circle and it extends an arc L. The plane angle theta, if the radius of the circle is r, is straight away L by r, the arc length to the distance of the radius. So the plane angle is very straightforward, and the solid angle is also quite straightforward after what we discussed today. Now let's take another question for the solid angle itself. So what is the calculate solid angle subtended by an octant. Octant means 1/8 of the complete sphere. of a sphere at the center of sphere. So it's very straightforward. So the solid angle is nothing but the area by the radial distance square, and the area is 1/8 of the surface area. The total surface area is 4 pi r square. We know that very well, by r square. So it will come out to be pi by 2 steradian for this case. Okay, now moving into the further questions, I would like to discuss a few important concepts. So we discussed about absorption and scattering in the last weekly live session, and scattering and absorption happen to be very prominent energy matter interactions at the level of the atmosphere. We also discussed about atmospheric windows, uh, which effectively means that there are some particular wavelength ranges through which the transmission or the transmittance is usually high of the radiation, which we call as the atmospheric window, which primarily lies in the visible region, that is from 0.4 to 0.7 micrometers, and some near infrared regions also. And that is why these regions are prominently used across many remote sensing based sensors. So let us see this diagram. A part of the radiation will come from the sun, which is finally detected by the remote sensing sensors. So what goes on in between? The first part is the solar irradiance, which is basically downgoing. It is firstly experienced by the top of the atmosphere. The T theta naught is basically the transmittance. So only some part of it will be transmitted. The radiation which comes downward into the Earth's surface. Then there is also some sort of radiation which undergoes some diffuse sky irradiance, which is primarily in the form of scattering as well as absorption. The absorption is because of the presence of certain molecules, and scattering we know is because of the is primarily governed by the particle size as well as the wavelength range. Then, after either diffuse sky irradiance or by transmittance to the atmospheric layers, this is primarily felt by the surface body. So, this surface body again reflects back the radiation. It again goes through some sort of transmittance and finally is being felt by the sensor. Some part of the radiation which came downward from the sun to the top of the atmosphere gets reflected back again and it's felt by the sensor again. We know that this scattering is more prominent in lower wavelength bands like the blue band than the near infrared or the red band, and that is why this part will be dominated by the blue range of the spectrum of the electromagnetic spectrum. Some part of it, as shown in 5, is primarily the reflected radiation which goes from one neighboring area into the other neighboring area. The other neighboring area in our case is the steady area, which will again get reflected through the atmosphere and will be finally sensed by the remote sensing system. So there are primarily several pathways. Pathway number 1 is directly from the solar radiation through transmittance of the earth, and it's being felt by the steady area. Pathway number 2 is primarily experienced by the atmospheric constituents, which again gets back to the sensor. So pathway number 2, you are not even getting to know the spectral features of the steady area. Then there is pathway number 3, which firstly in which the light rays firstly experience some diffused irradiance due to the due to the atmospheric constituents. Then they are down reflected into the steady area, and then it gets reflected back again. Then there is pathway number 4, which primarily does not even get to the steady area, but it gets reflected from a neighboring area and is finally sensed by the sensor. And then the pathway number 5, which gets reflected back from the sensor, from the neighboring area into the study area, and then gets reflected back into the surface. And the atmosphere as that, and everything, I mean, the primary energy interaction, energy travels through the atmosphere, which is primarily of around 60 miles of thickness, which is around 100 kilometer. So this is a huge this is an extremely thick layer of atmosphere through which the interaction with the atmosphere happens. So you finally receive something at the sensor, which is the total radiance at the sensor. It is primarily the summation of uh, the total radiance from the target of interest towards the sensor plus the path radiation, radiance from multiple scattering based interactions. So I will just give a brief about it before proceeding with some more numericals. Yes. So, firstly, we will talk about the interactions which happen at the level of the atmosphere, the energy matter interaction. We discussed that the two common or prominent interaction patterns in this case are scattering and absorption. Scattering is definitely a function of wavelength lambda and particle size. Let us denote it as d. So the scattering primarily is of three types: Rayleigh scattering, Mean scattering, and last is the non-selective scattering. It is due to the Rayleigh scattering that we observe the sky to be blue. Non-selective scattering is primarily white in color. We observe the clouds to be white and a foggy day to be whitish because of non-selective scattering. Non-selective because it scatters almost all the colors equally. And if all the intensities are equal of different color bands, we will see that as white. Okay, so Rayleigh scattering is directly proportional to 1 by lambda to the power 4 or inversely proportional to the fourth power of the wavelength. So this primarily makes the scattering much more for the smaller wavelengths than the larger wavelengths. It is due to this reason that you will observe the blue band scattering to be much larger than, let us say, the red band scattering. Okay, and in Rayleigh scattering, the dia, the particle size dia, is much less than that of the wavelength. In sorry, in Mean scattering, the particle size, yes, the particle size is almost equal to the wavelength, and in non-selective scattering, the particle size is larger than that of the wavelength of the radiation. So this is about scattering. What about the absorption? The absorption is basically the absorption because of the different constituents of the atmosphere, like the ones which I am showing in this figure. So there are different prominent constituents like water vapor, CO2, O2 and O3, N2O, which because of its absorption only allows a particular wavelength spectrum to pass through them, which is technically known as the transmittance. And because of that, the solar radiation which you will be observing at the surface will not be equal to the solar radiation which will be observed at the top of the atmosphere. So it is primarily because a lot of these constituents absorb some part of the solar radiation, rendering only a certain part to be available to us at the surface. So the sensors, the remote sensing based sensors have to be can only be designed for these particular wavelength ranges, which primarily allow for the transmittance of the radiation, which we technically call as the atmospheric windows. So absorption, we also know about the atmospheric windows. Atmospheric windows are the particular spectrum of wavelengths which allow for a fair amount of transmittance through them. That is, the transmittance is high through the atmospheric windows. Now let's take an example out of it, a numerical example. Okay, so what uh, what would be the magnitude of scattering of blue light, let us say of zero point 0.4 microns wavelength, with respect to near infrared light. So near infrared, let us say, is around 0.8 microns. So how would you solve it? I mean, we know that the scattering is primarily inversely proportional to the fourth power of wavelengths. Okay, so let's compare. Let's compare between blue and near infrared lights. So blue would be 1 by 0.4 to the power 4. NIR will be 1 by 0.8 to the power 4. So this will be 0.8 to the power 4 by 0.4 to the power 4, which is 2 to the power 4, so 16. So this indicates that the scattering from blue light will be 16 times greater than scattering from the NIR light. Now another thing, when dealing with a medium like air, which the energy particles always deal with during remote sensing based observations, uh, absorption and scattering are frequently combined in modeling purpose into an extinction coefficient. Let us term it as K. So the transmission, I mean the amount of radiation which can travel finally through these atmospheric constituents, despite the amount of scattering and absorption, would be actually proportional to 1 by the extinction coefficient times the thickness of the layer. So larger the thickness of the layer, smaller will be the transmission, and larger the extinction coefficient, smaller would be the transmission. Now this atmospheric layer is primarily around the thickness is nearly 60 miles or 100 kilometers. So it is quite thick actually. So there is always a chance that a part of the information, the energy based information, which we want to sense through the remote sensing based sensors, may actually not be coming into the sensor for detection. Okay. Another thing, the remote sensing sensors. Okay, someone is trying to enter. Remote sensing sensors can only operate in regions, I mean by the wavelength ranges where there are atmospheric windows. So there is no point of designing a remote sensing based system if you cannot actually detect it, and the detection can only happen, or the transmittance can only happen where through some particular range of wavelengths, which we term as the atmospheric windows. Another point, solar irradiance, I mean the incoming radiation, is reduced at sea level, I mean at the surface, by several factors like atmospheric interaction, scattering, and reflectance. So we discussed about the atmospheric interaction and atmospheric absorption and scattering already. We will also discuss about the reflectance in the next slide. Now coming to the part on reflectance, it primarily depends on the reflecting surfaces. It also depends on several other factors like the orientation angle of uh, the orientation angle of the sensor or the illumination at that particular time. But at this moment, we will just look at the reflecting surfaces as one of the dominant factors of reflectance. So there may be four possible types of surfaces. The first kind of surface is let theta I be the angle of incidence, let theta E be the angle of exitance, and let this be a smooth surface like smooth water. So these are known as perfect specular reflector, these kind of surfaces. Now the other kind of case may be of a near perfect specular reflector. So how would that be? So this is again theta I or the angle of incidence, and this is the theta E or the angle of exitance. But in this case, apart from a specular reflection, some part of diffusions also happen. So this is a near perfect specular reflection. Next up is, I mean, as we move into the third class would be one in which there is more diffusion. It primarily happens in the land surface through forested regions or vegetation. Okay, so these are known as near surface diffuse reflector, mostly happens in the vegetation, and that is actually mostly the case for the earth surface. And finally, a very idealistic case, which is a perfect diffuse reflector. It gets reflected equally in all the directions in perfect diffuse reflector or Lambertian surface. Now I would ask you one thing. What do you think among these four different surface types, which one is the most desirable for a remote sensing scientist? Any idea? I mean, if you want to say anything, feel free to unmute yourself and comment.
Sir, first one.
Ideally, yes, right? Why do you say that?
Sir, because it is a perfect reflector, no?
So no energy is lost. That's what you want to say, right?
Yes, sir.
Okay. Actually, it's the exact opposite. I mean, it goes opposite to the logic. I also used to agree with what you used to say. Okay, Rahul is saying the number 3 one, near surface diffuse reflector. Rahul, it is actually the perfect diffuse reflector or Lambertian surface. I will tell you why. ideally speaking, what the first speaker told was correct. I mean, ideally, it should be the perfect specular reflector in which the incoming uh, radiation is not getting diffused at all. But we are more interested in Lambertian based surface, which is an idealistic case. Why? I will tell you. The Lambertian surface also gives you an indication about the colors of the surfaces, which you cannot get through the perfect specular indicator. So what happens in specular indicator is that all the radiation which came will be oriented equally in the same direction. So the if the light which is white in most of the cases, the returning radiation will also be white. So you will not get to know about what kind of color of the surface there is. You will only get to know about it through the Lambertian surface. Why? Because all the particles have a particular capability of absorbing a wavelength of a particular wavelength. So whatever gets reflected back will not contain the characteristics of the absorbed wavelength range, and that is how you will get to know about a particular color of that surface. That happens only through a Lambertian surface. So white incoming, white outgoing is the one which happens in specular reflector, whereas white incoming and colored outgoing is the one which happens in the diffuse reflector. So that is why the Lambertian surfaces are more desirable. It goes against the logic, I can understand, but the color is a very important part of remote sensing based analysis, and that is why the Lambertian surfaces are thought to be idealistic. However, we don't see them in nature. They can be simulated in some experimentally in some labs uh, for some calibrations of the remote sensing based devices. So we are usually mostly dealing with only near surface diffuse reflectors, which or near perfect specular reflection. I mean, even this is a very less abundant scenario. We mostly primarily deal with near surface diffuse reflector itself. It also gives you an indication of the color because the constituent will absorb some colored wavelengths anyways. So that is what I wanted to discuss. Let's move to the next topic. If you feel like asking anything, I mean, you may unmute yourself anytime and ask me a question about it or anything else. uh,
Okay, sir.
yeah, thanks. So the first case was that there was a specular reflection. The surface is essentially smooth. It is almost smooth, and that is why there are no diffusions. And in this case, the average surface profile has to be very less than the wavelength of the radiation, incoming radiation coming to the surface. The second note is that if a surface is rough, then reflection rays go in many directions depending on orientation of smaller reflecting surfaces, which is known as the diffuse reflection. Now, if the surface is so rough that there is no individual reflecting surfaces in them, then scattering may also occur. Finally, about the idealistic surface, that is the Lambertian surface. For the Lambertian surface, the radiant flux leaving the surface is constant for any angle of reflectance to the surface, and that is why Lambertian surfaces are thought to be desirable. However, they are extremely idealistic. Any kind of surface will have some impurities which will render them not to be Lambertian. And finally, I mean, why do we need the diffuse radiation? Why? That's the same part which I discussed just now. Because diffuse radiation gives us the information about color as the object absorbs some wavelength. So whatever is reflected will not contain the signature of the absorbed wavelength, and that is how you get a color, even though the incoming light is just white in color. However, in specular reflection, you don't get any information about the color. The the specular reflection doesn't give us any information of the color of the object. Now let's come into some of the basic parameters which we discussed in the first 2 weeks of this course. The first one is the radiant flux density. It is always defined for an area on the surface of the earth. Okay, let us suppose this is a surface. The radiations are incoming to the surface, let us say. So the radiant flux is phi lambda. Lambda because it is a function of the wavelength also. So the irradiance, which is the incoming radiation, is represented in terms of watt per meter square. It is the radiant flux density is basically phi lambda by A, because it is defined for a particular surface area. So the irradiance is basically the amount of radiant flux incident upon a surface area. What happens with the exitance? There is another term which is known as the exitance. It is also defined with respect to the radiant flux itself. So after a reflection, some part of the radiation will be again going back into the atmosphere. Let us suppose the radiant flux for that case is also phi lambda. So the exitance, which is sorry, someone is trying to enter. Exitance, which is the radiation leaving a surface, is, let us say, m lambda, which is phi lambda by A, and it is measured in terms of watt per meter square. Now the radiance, another very important parameter, which is finally detected by the sensors of the satellites, and that is why it becomes very important. So the radiant flux is defined as radiant flux per unit solid angle leaving an extended source in a given direction per unit projected source area in that direction. So these statements all boil down to a particular equation. The radiance L lambda is nothing but the phi lambda by the solid angle by A cos theta. Cos theta because it is a projection for that angle, and this radiance is measured in terms of watt per meter square per steradian. Steradian is a solid angle. A is the area, projected source area. Theta gives you an indication of the direction, and omega is, we know well, is the solid angle. So now let's move back into the basic figure which I showed here. So there are paths 1, 3 and 5 in the same figure. Paths 1, 3 and 5. What are these paths? Let's see. So this is the first path, this is the second path, and this is the fifth path. So these will give us an idea about the radiance from targets, spectral information. 1, 3 and 5. Why? Because they all are able to reach the study area somehow. Okay, now let's look at paths 2 and 4. This is known as technically known as path radiance, depicted as LP. So this is primarily the diffuse sky irradiance. 2 and 4. 2 and 4. So these paths never actually are able to reach the study area. So this is basically the diffuse sky irradiance or radiation or radiance from neighbors, but not from the target. Now what about path 1? Path 1 is the one which passes through the atmosphere and then reaches the study area directly. So this is basically the spectral solar irradiance, and it depends on the zenith angle theta naught. Theta naught is this. So it depends on the zenith angle, and of course on the atmospheric constituents also. That is given by T theta naught, which is the transmittance. Let's discuss that too in the next slide. I will add an additional slide here. So path 1 is spectral solar irradiance and depends on solar zenith angle theta naught. So amount of irradiance which coming to the terrain, terrain is the target body, depends on atmospheric transmittance. I mean, how much amount of the radiation will be allowed to move through the atmospheric constituents, either by scattering or by absorption. Which is T theta naught. Now T theta naught would be exactly equal to 1 if there is a perfect atmospheric window, but we know that is not possible. As you can see that the top of the atmosphere solar radiation is never equal to the one which reaches to the, let us say, the sea level or the surface body. Now talking about path 2, Path 2, at as you can see, is the one which never reaches the surface. It gets diffused because of the atmospheric constituents. So it is something known as the spectral diffuse sky irradiance. Spectral diffuse sky irradiance. We denote it as ED2, let us say. And it happens because of due to scattering in the atmosphere. And scattering, as we discussed earlier, happens more for the smaller wavelength ranges. And among the visible bands, that is blue, green, and red, we know very well that the blue band has the smallest wavelength. So the scattering would be the largest for blue band. So one thing which you will always observe, I mean, in some due course of time, you will be probably using remote sensing based products. You will mostly observe that the uncorrected bands, I mean, the bands which have not been corrected for atmospheric corrections, the atmospheric absorption and scattering, they will always have the blue band as the brightest. Why? The blue band is as brightest because the scattering is the largest through the blue band, because the scattering is inversely proportional to the fourth power of the wavelength. So smaller the wavelength, more will the scattering, and that is why more information will be received in the blue band because of this issue. So the implication of this is that blue band images by remote sensing sensors are much brighter. Why? Because of the higher scattering in this in this color of band. Okay. Now let's move to path number 3. I'll take another slide. Path 3. Let's go back. So the path 3 is the one which firstly gets diffused by the atmospheric constituents, but then it falls on the target area. So path 3 is technically known as the downward reflection reflectance of the atmosphere. Downward reflectance of the atmosphere. It is also a function of the wavelength. That is why the subscript lambda comes in. Path 4. Path 4, we go back again. Path 4 does not fall on the target surface at all. It gets the radiation only moves from the neighboring area into the sensor again. So path 4 is basically the reflected or scattered by nearby or neighboring terrain, governed by the reflectance rho lambda u into the IFOV, instantaneous field of view of the sensor. Okay, so one thing which you observe is that paths 2 plus 4, what's happening there? Paths 2 and 4. So path number 2 and path number 4, they don't meet the target at all. They're just going back into the sensor again. So these we term as the path radiance. Let us suppose we term it as LP. Finally, path 5. Path 5 is the one which is reflected back from the terrain, the nearby terrain into the target area and then goes back into the atmosphere and detected by the remote sensing sensor. So path phi is basically reflected from a nearby terrain into atmosphere, into the target area, and then into the atmosphere, but then scattered or reflected into the study area. So let's come back into the total radiance. We are actually, I mean, the reason of showing these different paths was that we primarily, as remote sensing researchers, are interested at the amount of total radiance which is received at the sensors. We finally can only do our analysis and measurements with the radius which finally receives is finally received at the sensor. So how to quantify that? Let's see. The total radiance reaching the sensor from the target, the one which we are actually requiring, is, let us suppose we term it as LT, 1 by pi over a particular wavelength spectrum, let us say lambda 1 to lambda 2, the reflectance, the transmittance, E O lambda T theta naught cos theta naught plus ED D lambda. Okay, so this is the diffused pi part, the diffused sky part, and this is the other parts basically. I will explain why this 1 by lambda comes in the radiance calculations. I will explain it in probably 10 to 15 minutes from now. So the total radiance recorded by the sensor will not only be the total radiance which reaches the sensor from the target, but also the path radiance part. So let us suppose we are terming it as LS. So LS is LT plus LP. LP is the path radiance and LT is the total radiance which reaches the sensor from the target. And LP, we all know, is the one which does not reach from the target, so it will not give us a spectral information about the target. So LS can be H rho T plus LP. I will tell you what these terms are. LS is the radiance at sensor radiance. H is the total downwelling radiance. T rho is the reflectance of the target. A part of it will be absorbed and a part of it will be reflected. So the reflected part is shown by the reflectance. Sorry. T is the transmittance, atmospheric transmittance. So whatever part is reflected back will again be transmitted by the atmosphere. So this is the atmospheric transmittance, primarily in the region of the atmospheric window. And LP is the atmospheric path radiance and depends on the wavelength lambda. So let's take a numerical out of it. Uh, yeah. So the question states that the spectral radiance from the object after all interactions is, let us say, 28 watt per meter square per steradian per micrometer, and the atmospheric transmissivity is 0.72. Then, and the final radiance at sensor is, let us say, 29 watt per meter square per steradian per micrometer. So what is the path radiance? So it's very easy to solve. We know that the total radiance which is recorded by the sensor, LS, is the total radiance which is observed by the sensor from the target plus the path radiance. Yeah, plus the path radiance, and the path radiance is a function of the wavelength. We discussed it just now. So what would be the path radiance? The path radiance would be Ls minus Lt. Ls is given as 28 watt per meter square minus watt per meter square per steradian per micrometer minus the transmittance, that is 0.72 times 28, and this will come to be 8.84 watt per meter square per steradian per micrometer. So we just use the same equation which we discussed in the previous slide, a few slides from now, and using this we came to the calculation of the path radiance. Let's take a few more examples. Another thing, for any body, let us suppose there is any body, the reflectance, the summation of the reflectance plus the transmittance plus the absorptance has to be equal to 1. So reflectance means that the amount of radiation which is reflected out of the body by the initial radiation out of the body. Transmittance means that the amount of radiation which can be transmitted from the body divided by the total amount of incident energy into the body. And absorptance means the amount of radiation which can be absorbed by the body to the incident total radiation on the body. So we, let us suppose, ER by EI plus ET by EI. EI is the incident radiation on the body, plus EA by EI equal to 1. This is what it states. So this transmittance can only ideally happen in bodies which are not opaque. If the body is completely opaque, then the transmittance will be 0. The reflectance will also happen in particular object types. For example, for vegetation types, there are two peaks in the reflectance curves. The first peak, but a smaller peak, happens in the green band, whereas in the red band, and the second peak happens in the near infrared band. So let's take a question. What would be the absorptance of an opaque body with a reflectance of 0.6? So the body is opaque, so we can straight away say that the transmittance, it will not be able to transmit any light through it. The transmittance is 0 because the body is opaque. So A plus R plus T is equal to 1. I'm straight away talking about this equation. T is anyways 0. So this leaves us with the absorptance as equal to 1 minus the reflectance. So it is 1 minus 0.6 equal to 0.4. Okay, let's take another question. Let us suppose it's given that the spectral radiant flux density reaching the surface is equal to 500 watt per meter square. The reflectance of the body is given as 0.33. Let us say it is 0.33. Then what would be the spectral radiance leaving the object after interaction with the body? Okay, so the answer is very straightforward. The reflectance is given as 0.33. So we can, I mean, since nothing is given in the question, we can assume that this is a Lambertian surface. So that spectral radiation leaving after the interaction would be nothing but 500 watts per meter square times the reflectance by pi, just the case which we used a bit earlier. Yes, this part. And this would come out to be 52.52 watt per meter square. Now, I would like to discuss why this pi term comes in the denominator. What is so special about it? Let's discuss. Let us take one sort of a point source, an example of a isotropic point source. So the isotropic point source by definition is the source which emits light in all directions, and since it is in all directions, it assumes spherical symmetry. So let us suppose the radiant power for such a case is given as radiant power denoted by, let us say, phi E source is given as 10 watts. So what will be the radiant intensity? So the radiant intensity is IE, which will be equal to the radiant power phi E source by 4 pi steradian. Why 4 pi? Because a spherical object subtends and a solid angle which is equal to 4 pi at this end. So it would be 10 watts by 4 pi steradian, which comes out to be around 0.80 watts per steradian. However, we observe that we don't get a 4 pi in the denominator. We actually get a pi in the denominator. So how did that come to be? Let's discuss that further. Let us suppose for an infinitesimal surface element, the area is dA at distance, at let us say a distance equal to r, and perpendicular to the beam. Solid angle we know would be, solid angle subtended would be, let us say, d omega is dA by r square. We are very familiar with this equation by now. So what would be the infinitesimal radiant power? Let us denote it as d phi. It will be I times d omega. It is phi e source radiant power by 4 pi steradian into dA by r square equal to phi e source by 4 pi r square times dA. So we will get the irradiance at a distance r equal to, let us suppose we denoting it as E is equal to phi E source by 4 pi r square after integrating it over the entire surface. So this gives us an idea of the irradiance being directly proportional to 1 by r square, or the inverse square law. And this will be valid only if the distance, valid only if and only if the r, that is the radial distance, is much greater than the geometric dimensions of the source. So we again write the equation is sorry, my slide is not working for the time being. Just a second. Oh, I need to use another slide. I will write it in the next slide. So this was the case of uh, an isotropic point source so far. So for that there will be 4 pi in the denominator but not pi. But how did we come to a pi in the denominator? Let's take it. So when it is a spot source, which is mostly the ones which we find in nature, spot source are not spherically symmetrical, because most of the objects which we consider are not spherical and definitely not symmetrical. So they are primarily like spots. The irradiance will be source by pi r square, not the 4 pi r square. I will derive it in 2 slides from now. Okay. Now let's talk about a Lambertian surface. So the speciality about Lambertian surface is that it either emits or reflects radiation with constant radiance LE in all directions of a hemisphere. Okay, let's take it in the next slide. So what would be the directional distribution of a radiant intensity? Let it be IE, which is a function of the theta, IE 0 angle projection times cos theta. So, but IE 0 would be integrating it over the entire region, cos 0 degree dA over the entire emitting surface profile, which will lead us to LEDA over the entire emitting surface. So this IE theta is primarily the radiant intensity emitted in the direction perpendicular to the surface, and theta equal to the angle with the surface normal. So the surface exitance is nothing but ME is LE by pi when we basically integrate it over the entire region, and that is why this pi in the denominator comes to be. And this is primarily like this. Uh, ME is over the 2 pi steradian region, not the entire 4 pi one, because it is not a total sphere. LE cos theta d omega, which will come out to be after several mathematical manipulations, LE by lambda, and that is why we get the lambda uh, in the denominator. Now let's take an easy question related to this. There is a flat horizontal Lambertian surface. The total radiant flux intensity from object is given as 200 watt per meter square. What is the radiance reflected by the object? So we know that the exitance and the radiance are linked by this equation. So ME is the one which is required. It will be 200 by pi, which is equal to nothing but LE by pi. It comes out to be 63.66 watt per meter square per steradian. Coming to the last part of today's discussion, another a bit mathematically rigorous way to link M with L is like this. Let us suppose we are trying to relate the exitance with the irradiance. It can be done like this. There is a surface, the surface area of which is dA1. Let us project a normal, an outward perpendicular normal out of it. and let us subtend a solid angle of the incoming ray out of it. The surface area of it, let us suppose, is an infinitesimal surface area dA2 phi, and it subtends an angle theta with respect to the perpendicular of the area with that of the body. So the area element of the sphere of radius r, let us suppose, is dA2, which will come out to be r d phi r sine theta d theta, which is r square. I mean, these two r's get multiplied. Sine theta d phi. Now the first step to relate m lambda, that is the exitance with the irradiance, would be to start with the radiance. Start with radiance to get flux within area dA2. So how do we do that? Let's see that in the next slide. So L is a function of theta and phi. It will be given by a derivative d phi by dA1 cos theta d of the solid angle, the infinitesimally small solid angle. So d2 phi is L function of theta and phi times cos theta dA1 d omega equal to L theta and phi cos theta dA1, and omega can also be written in terms of the surface area dA2 by the radial distance r square, equal to L theta phi cos theta dA1 sin theta d theta d phi, because sin theta is a projection on it. So this implies that the total flux in the hemisphere above the source will come out to be, when we integrate it over the different thetas and the phi, possible thetas and the phi, it will come out to be phi, which is dA1 d phi, which will vary from 0 to 2 pi and 0 to pi by 2 of d theta, L theta comma phi cos theta sin theta d theta. Now it is pretty clear that theta can only move from 0 to pi by 2, 90 degrees, and phi can move from 0 to 360 degree, which is nothing but 2 pi. Okay, so in general it is equal to L theta phi, but for Lambertian surface L is a constant. In general, L is a function of both the angles, but for Lambertian surfaces it is a constant. So for that case, we can take out L from this expression. The final expression would be 2 pi L sin theta whole square by 2 integrating over 0 to pi by 2, which will come out to be pi L dA1. So this gives us that the radiant exitance is equal to, let us say, m is phi by dA1 and m comes out to be pi l, and that is why you get I will show in the next slide. And that is why you get the if you include the spatial include the spectral variation also, because these radiances are actually functions of wavelengths also. M lambda, the excitance will be pi l lambda, or l lambda is m lambda by pi. So that's it for today, but I will try to wrap it up with a brief revision of whatever we discussed today. Okay. We firstly took a numerical on the total solid angle subtended by the sphere at its center. We understood that steradian is basically a unit to quantify the solid angle. Unlike the plane angle, which is the ratio of the arc length to the radius. So we found out that the total solid angle subtended by a sphere at its center is basically 4 pi steradians. Then we took some cases. We got to know the solid angle subtended by a point symmetrically at a particular radial distance from a particular area. We did that numerical. Then we took a common general case of an octant of a sphere, and we understood that the solid angle for that case would be pi by 2 steradian. Finally, we discussed in details about the energy matter interactions in atmosphere through the steady area, that is the one which I am depicting to right now, and the satellite sensor detector. Ideally, the satellite sensor detector should only include spectral information about the target area, but that doesn't happen actually. A part of it goes as path radiance, a part of it again goes reflected from the neighboring area into the steady area, and then goes back through the atmosphere to the sensor. So there are several complexities to this problem. So we finally found out that the at sensor radiance is basically the total radiance which is received by the sensor from the target area plus the path reflectance. We also discussed about the different kinds of interactions in the atmosphere. The two prominent interaction patterns are scattering. Scattering happens to be a function of the wavelength as well as the particle size, and absorption. Basically shows that the transmittance through the atmosphere can only happen in some particular wavelength ranges. Uh, so 0.4 to 0.7 micron, you can see it basically transmits quite a lot of the radiation, and that is why we can design any sensor on the wave on the visible spectrum at least. Also, there is a fair amount of transmittance to the near infrared and some far infrared zones, and that is why many sensors also exploit the near infrared and the thermal infrared zones uh, for the detection. We finally took up a problem to quantify the scattering of a particular wavelength of light with respect to some other particular wavelength. The scattering we know is inversely proportional to the fourth power of the wavelength. So smaller the wavelength, more would be the scattering. This also was the reason why for blue bands of the satellites, uh, the blue bands of the satellites are usually brighter than the other bands of the satellite. So we need to transform them through a correction factor before using them for our own purpose. The transmission we also understood was basically inversely proportional to the product of the extinction coefficient. Extinction coefficient is basically uh, a quantification of how much of the atmospheric absorption and scattering will affect the radiation moving through the atmosphere, and it is also multiplied by the thickness of the layer. So the thicker the atmosphere is, uh, the lesser would be the transmission. The atmosphere in general is around 60 miles thick, which is around 100 kilometers of thickness. The remote sensing sensors can only operate in regions where there are atmospheric windows. So we need to design the sensors only for some particular sensing some particular wavelength ranges. Visible range is one such particular wavelength range. The solar irradiance is reduced at the sea level by atmospheric absorption, scattering, and reflectance. We then got to see the four different cases of reflectance through the surfaces. Uh, we moved from a perfect specular reflector to a perfect diffuse reflector. We got to know that although the energy lost is lesser through a perfect specular reflector, but the desirable kind of surface type is a Lambertian surface because it gives an indication of the color of the surface. Because in the perfect specular reflector, the incoming white light will only be reflecting a white light again. You will not get to know about the surface features or the colors, which you will get to know in the Lambertian surface easily. Now, if a surface is rough, the reflection rays go in many directions depending on the orientation of smaller reflecting surfaces, which is what we call as the diffuse reflection. Of course, these reflections will also be dependent on the orientation of the camera, the viewing camera, or the sensor from the space. It will also depend on the kind of irregularities. It will depend on several factors, by the way. It will also depend on, let us say, amount of water present in the vegetation, the amount of stress in a vegetation, and several other factors. You will be learning it in probably 1 to 2 weeks from now. We understood that the Lambertian surface is basically the one in which a radiant flux leaving the surface is constant for any angle of reflectance to the surface. And why do we need diffuse radiation? Because it gives us an information about the wavelengths. Then we got to know the relation between the radiant power and the irradiance, the excitance also, the radiance. We finally got to know the total radiance which is incoming to the sensor is basically the radiance which comes from the target area plus that of the path radiance. We took up a numerical about the same. We also understood that the summation of the reflectance, the transmittance, and the absorptance from a particular body is equal to 1. Because a particular body can only, do these three features with the radiation incoming to it. And if a body is opaque, then the transmittance will of course be 0. So we can straight away find the absorptance using 1 minus the reflectance quantification. Finally, we took up a numerical to relate the spectral radiant flux density with that of the excitance. We found out that it's basically related with pi in the denominator. We understood that for an isotropic point source, there will still be 4 pi in the denominator. However, when there is a point source or a surface, then the spot source will have only pi in the denominator, which would be the case for a Lambertian surface. We then took up a derivation to understand the same. The derivation indicated that finally the excitance is pi times the irradiance, or the irradiance is excitance by pi. So that's it for today. If you have any question, then please feel free to ask me. Is there any question from this part? Kindly unmute yourself and ask, or you can even type it in the chat box. Okay, Rahul. Anyone else? Okay, Mansi. Anything you want to ask from the entire lecture, or maybe something else from this course? Please feel free to ask me. Record lecture will, yeah, I've already provided it on the YouTube channel. The link was given here. This is the link which will contain the lectures, the slides, as well as the link for the YouTube video. I have made a playlist, and I have already uploaded the first video from the weekly live session number one in it. Sorry. Anything else? Regarding any JRF position, I asked, sir. Okay, keep checking the vacancies in that case. I mean, on the website itself, they are quite transparent, so you can keep checking the vacancies on the websites, and you will get to know about that. Anything else? I mean, from the course or anything else? Okay, so I think that's it for the day. I shall stop recording it.